Hey folks, so we're back here to talk about master theorem. So we saw last time that solving recurrences is possible using some clever tricks, and then we can prove that correct using induction. But we probably didn't want to do that every time we ran into a recursive divide and conquer style algorithm. So what I'm going to show you now is kind of a shortcut that works most of the time. Yeah. Okay, so this shortcut, you may have seen this before. It's called master theorem. Obviously, the previous method's fairly difficult, but this guy is going to give us an easier way to approach these. Specifically, so merge sort. Let's review what we saw last time real quick here. We divide the array into two halves. We recursively sort the two halves. And when we have a linear runtime to merge them. So our cost looks something like this, right? I'll skip worrying about like this constant, right? Let's just treat it like n. All right, let's just treat this as linear as opposed to a constant times linear to keep it even simpler. How would we analyze this guy if we don't have the previous tools, right? How would we analyze this in a way that lets us skip doing all that stuff? Well, that's where master theorem comes into play. Let me see. It shows up a little bit small. Here, I'll show you this on Chrome. A little bit better. Okay, let me move my mic closer and just go over the idea of master theorem for you. Master theorem, it turns out, applies to recurrences of the form a times t of n over b plus f of n, right? So if your recurrence has like this format, there's a good chance you'll be able to try master theorem on it. We'll think about when that doesn't work maybe a little bit later. But for now, yeah, most of the time you'll be able to try master theorem to work on this guy. There's some restrictions though. A is kind of the number of recursive calls being made of type n over b, right? And so probably it makes sense, you need to have at least one recursive call. A has to be greater than or equal to 1. If you had less than one recursive call, then it would be like, wouldn't be recursive, right? If you had 0 recursive calls. So it doesn't really make sense for this to be anything other than greater or equal to A. I think that one's straightforward. B, though. B is how much you're dividing by in each of your recursive calls. Needs to be the same across every recursive call. Same division. And we say the division has to be by at least, or has to be by more than 1. Not just at least 1, like with A, but more than 1. Huh. Okay, that's weird. Well, it makes sense that we shouldn't probably divide by 0. But what about dividing by 1? Why don't we allow the divide and conquer algorithm to divide by 1? Again, think about it if you need to. That wouldn't really, that wouldn't make a very good divide and conquer algorithm if you think about it, because we really need to reduce the problem size. If b was 1, then t of n is being defined in terms of t of n, right? You're not accomplishing anything. You're just, rewriting t of n as t of n, yeah? And actually that means your algorithm would be an infinite loop because you're never solving anything. Yeah. And then the last one here, this one's maybe the trickiest. It says that f is asymptotically positive. So what it's trying to get across is that f is not allowed to be a weird function. It has to be a function that continually grows as n grows. Just to give you an example of something that would not be so good. Swap back to DocCam. So the kind of thing you wouldn't want for f of n that would be a little weird would be like a sine function, right? you had like a sine function relative to the input n, then the runtime doesn't just strictly increase as n gets bigger. Sometimes the runtime gets smaller as n gets bigger, which doesn't make a lot of sense. If n is your input size, we want a function that grows as n grows, or at the very least stays equal. So it could be a constant, like a runtime of 10 that stays 10 forever, but it shouldn't be something weird that goes up and down and whatever, does that kind of stuff. Okay, so there's your conditions for applying this. And just for fun, let's look at what's coming up here. So I actually have merge sort being used as the example, conveniently enough. So here's the master theorem. This is a really good slide in terms of summarizing what the master theorem is about, the three major cases that we consider. But I think it's not a good slide in terms of being comprehensible to the human brain. So I'm not going to worry about this slide. I'll just say that once you understand the master theorem, this guy is a good slide to look at to summarize what it is. Let's instead go down to the bottom here and consider on these guys, these are a little bit more readable. Let's consider the cases. All of our cases have to do with comparing the f of n from up here, to n to the log base b of a. Yeah, all of them are comparing these two guys. Why n to the log base b of a? Well, we don't really need to worry about that here exactly. Like, we're not going to prove the master theorem, but the intuition is this represents the recursive runtime. Yeah, and f of n represents the non-recursive runtime. So in a sense, what we're doing is comparing which is bigger, the recursive runtime or the non-recursive runtime. And then we have three different cases, which correspond to the recursive runtime being bigger, the non-recursive runtime being bigger, that's the omega case here, and case 2, which is that they're equivalent to each other. Yeah, those are our three cases. Swapping back to DocCam for a sec. So this is the non-recursive runtime, and this guy is the recursive runtime, right? And let's just try that out here. The master theorem slides are on the Blackboard, by the way, so if you want to pull those up as I'm doing this, feel free. So here's merge sort. F of n is easy, right? F of n is just n. But we also need to find what A and B are, right? A and B. Well, A is the number of recursive calls. So we know there's actually 2 recursive calls. And B, that's the size of the, it's like the amount we're dividing by in our recursive calls. So we're dividing by 2, right? So this is number recursive calls. This is size of recursive calls, and B is what we're dividing by in that size. And then once we have A and B, we need to figure out what n to the log base B of A is. N to the log base B of A will be log base 2 of 2, which we saw this in the previous set of notes. Log base 2 of 2 is just 1. So actually, in this case, which is bigger, the recursive runtime or the non-recursive runtime? Right, this is the recursive, this is non-recursive. Well, actually, they're both n to the 1, right? Actually, the same. And that would, the way we can say that is that the n, right, the n runtime for our f of n is tightly bounded by the n to the log base b of a, which is n to the 1, right? N to the log base b of a. So this guy is true, and I said while we were looking at the previous page, right, the master theorem notes, that was case 2. And I'll pull up the text one here. That's case 2. And, well, let's see, case 2, f of n and n to log base b of a grow at similar rates. And it just tells us the solution. It says that t of n will be in theta n to the log base b of a log n. Okay, so it says t of n is going to be in theta n to the log base b of a times log n. Well, if we work that out, this is just n, right? So there we go. T of n is in theta n log n. Proved, right? Once you've done with the master theorem, you're done. This is also a proof. So what was that? 11 minutes here or so. So it was like 11 minutes to introduce master theorem and use it to prove the runtime for merge sort, which took us like the better part of the last lecture to do. Okay. This is probably a good indication of why master theorem is handy, right? Is really fast once you get the hang of it. Let's do another case. Next case here. So we figured out what merge sort is. We confirmed our expectations of what that was going to be. Let's do another one that we saw last time, but I didn't actually formally analyze. Binary search. You could use the techniques we learned last class to analyze this guy and check my work here if you're so inclined. But I'm going to just use the master theorem to solve it. So let's just start off here. Maybe it's a case 2 as well. Who knows? That would make it easy for us, right? And then let's see, d of n. Again, I'm just going to ignore the constants. I wrote these in as a constant to make it slightly trickier, but we can just ignore it for now. This is just a constant factor. Let's see, our a is, let's see, well, I don't see a number here. So actually that tells you it's actually 1, right? There's no coefficient written there, but it's because we only have 1 copy. B is still 2, like the last one, and f of n, actually f of n is going to be 1 this time. And if we go ahead and find n to the log base b of a, well, it's going to be n to the log base 2 of 1, which is n to the 0, which is actually 1. So this is a constant. This is a constant, right? Actually, literally, because I changed it from d of n, it's literally the same constant. So actually it is case 2. Oh, that's lucky. Is it always case 2? This is great. It's not always case 2. But that worked out well for us because, yeah, it turned out binary search also is the exact same case. And again, that's going to be because the f of n is tightly bounded by n to the log base b of a. Log base b of a. And because that's true, that tells us that the total runtime, t of n, again, t of n is the total runtime, is going to be in theta, n to the log base b of a, I'll write it out again just in full, times log n. I'm just getting that from the paper, right? I'm not doing anything special here. I'm just literally looking at the paper and copying it down. Sorry if that's small again. I can swap over to the Chrome tab when we do the next one here. So that's going to tell us that t of n is in theta. This is just 1 times log n. Oh, okay, that makes sense, right? So t of n is in theta of log n, right? That's telling us that binary search takes a logarithmic amount of time. Something you probably already knew and maybe were shouting at the at the previous lecture while watching it, yes, that is the correct runtime. And Master Theorem shows it to us. Neat. Okay, let's try again. Let's do this. Example 1. I don't have code for this guy, but I could create some. You know, if you want to see some of these guys implemented in code, let me know in our in-class lecture, and we can do that. So A in this case, let's see, A is 4 for this one, right? B is going to be 2 again. A lot of 2's. And f of n is the square root of n. That's a little weird, but okay. We'll try it. We need n to the log base b of a, right? Which is, in this case, n to the log base 2 of 4. Log base 2 of 4. That's going to be n squared, right? Because 2 to the power of 2 is equal to 4. So 2 is going to be the result of that log. You know, nothing else. Master Theorem gets you much more used to the idea of doing logs, right? Which is a good thing. We use those all the time in sort of analysis of algorithms. Good thing to get used to. Well, are these the same? No, unfortunately, this is not case 2. We were on a real roll there, but not case 2. So, swapping over to Chrome, let's see if we can figure out which case this would be. Which of them is bigger? Well, look like n squared would be the bigger of them. So the recursive cost is dominant. That's actually case 1. You can see f of n is in big O of the recursive thing. There's another little bit here, that minus epsilon. We'll talk about that in a minute. But the important part is it's upper bounded by n to the log base b of a. Okay. Easy peasy. Let's write that down. So we want to prove, this is, we think, maybe case 1. Right, case 1. We think that we're going to prove that n to the 1/2, right? Square root is really 1/2. Square root is really 1/2. N to the 1/2, we want to prove that this guy is upper bounded by n to the log base b of a, so that was n squared. And then we had this weird minus epsilon, minus a weird looking e. Okay, so we need to prove this guy. And it turns out we need to not just prove it's true for any epsilon, we need to find an epsilon greater than 0 that makes this true. Okay. So we want to find something that we can plug in for epsilon here that will make this true. Well, you could just choose really small epsilons. You could choose, like, for example, epsilon equal to 1. If you plug in epsilon equal to 1, this becomes 2 minus 1, so this will be 1. And this is true, yeah, true for epsilon equal to 1. I tend to like to make it even more obvious. Like here, I know sometimes students struggle with, okay, which is bigger, 1/2 or square root or just regular? Which one's the higher growth rate? If you stare at it for a while, you'll realize actually this guy's going to grow faster. But you can make it even easier on yourself. We could just think about choosing epsilon to make it exactly equal. I tend to like to do this because I think it makes it a little bit easier. So in this case, if epsilon was equal to 1.5, then this would be 2 minus 1.5 as our exponent, which would then make this n to the 1/2 is upper bounded by n to the, well, this would be 0.5, which is 1/2, right? You know, another way to put it is like that, right? So if we subtract away 1.5 from 2, we're left with 1/2. Either of these would be right. Like, it doesn't matter. There's a lot of right answers. You could come up with more. You'd be like, well, epsilon could be equal to 0.00001. That would also work. You could keep coming up with more and more. Let me slide that up. You can keep coming up with more and more examples. But we only need to find one that's true. So this works. Any of these works to prove it. We've shown that these guys, this is still upper bounded by the recursive runtime, even if I remove some of the recursive runtime. What the epsilon is, this is remove an n to the epsilon factor. The logic being here, let me swap back to Chrome. The logic here being that we've just proven that f of n grows polynomially slower by an n to the epsilon factor. So we've actually found kind of an amount by which these differ, right? What we're trying to avoid is it being a case 2. Case 2, they grow in similar rates. Here, they do not grow in similar rates. Actually, they differ by at least n to the epsilon. So that's why this exists, is to avoid the n to the epsilon, or avoid the case 2 happening when it's actually a strictly faster growth rate, right? When it's a strictly faster growth rate, we actually want to find that difference. Okay, and then actually, because the f of n is growing much slower than the n to the log base u of a, like this guy is growing polynomially faster, that guy is actually going to be our dominant cost. It turns out it completely overwhelms the f of n cost, and our cost will just be n to the log base b of a. That's kind of cool. So we conclude from that t of n is in theta of n to the log base b of a, which is n squared. So this guy, the whole runtime for this thing is just n squared, and it's because of this n squared here dominating that square root of n. That's case 1. Very good. Try these out. You know, make up your own numbers after you get through these. You can come up with examples to try out for yourself and see if it makes sense. Of course, there's going to be a bunch more of these on the homework. So then example 2 here. We've got, again, an a equal to 4, a b equal to 2, but now our f of n is n cubed. Well, our n to the log base b of a is still n squared. Log base b of a is still going to be n squared from the logic from the previous page, right? That didn't change. But which of these is growing faster now? Well, it's actually the f of n, right? This guy is the faster growing of the two. And so if you go and you look for this is case 3, what we'll need to prove is that our f of n cubed is lower bounded, right? Not upper bounded anymore, but lower bounded by our n to log base b of a minus, plus some epsilon. Yeah, so let's check on that. So you can see in case 3, we're adding, again, some epsilon, and this is saying that the f of n now is growing faster by an n to the epsilon factor. Yeah. All right. So let's find an epsilon that works. Well, let's see here. So it's n cubed Well, what would be a simple epsilon to make this work? Well, actually, epsilon equal to 1 is pretty good, right? Because if we choose epsilon equal to 1, they're the same, right? Again, I like making them the same because once they're the same, it's like, yeah, obviously true. It's like, trivially, this is true. Trivially true. All right, that seems good. So are we done? This is where all the other ones left off, right? Case 1, case 2. Well, unfortunately, case 3 is a little weird. And you might have seen it when I pulled up the Chrome tab earlier. What you'll see is there's actually a regularity condition, which is just checking to make sure our f of n function doesn't do anything weird. Yeah, that our f of n function is growing as n gets bigger, f of n is getting bigger. And this is usually a very easy condition to run through. It really just takes like a second, but it's easy to forget because it's a weird case, right? It's a weird extra case. Okay, so let me write that down. Again, if you want to have the page open, you can grab it from Blackboard. It said that we want to prove that a times f of n over b is less than or equal to a constant c times f of n. All right, we want to prove this. Well, c is a constant we choose. So we choose this. So we're really trying to find a c that makes this true. Another way to think of it. Let me plug in the stuff we know. We know that a is 4, for example, and we know b is 2, right? So this guy, just this. F of n over 2. Do we know what f of n over 2 is? Well, we know f of n is n cubed. So f of n over 2, well, f is just a function that cubes whatever you give it, right? So we give it n over 2, it cubes n over 2. All right, that's just what f of n does. And, well, let's see here. That's going to be 4. We move that inside. This will be n cubed over 2 cubed, which will be 4 over 4n over 8. All right, 4n cubed over 8. This guy is 8. The 4 and the 8 cancel and gives us 1/2 n cubed. You see how that worked? So I just kind of, plugged in the stuff we know, evaluated the exponent, and then canceled out the stuff that was there. And what we got to was, well, this is a 1/2 times f of n, right? Because f of n is just n cubed. So we can choose c. We can choose c equal to 1/2. All right. That completes the proof. We basically, what this is saying is that f of n is more expensive the higher up you are in the recursive calls. Every time you go down a recursive call, you're shrinking geometrically by a factor 1/2. Yeah, you're shrinking by like a factor, at least a factor 1/2 every time you do a kind of recursive calls down the tree. And so the dominant cost of this is going to end up being just f of n by itself. The recursion actually doesn't contribute meaningfully to it. It's just going to be n cubed. And again, I can go through some of the logic of this. We could manually compute this using the techniques we saw in the last class, which might be useful. But for now, maybe that's good enough to get you started, at least to try some of these out and get stuck. So I did a case 1, I did a case 3. I guess we should do some more here though, just to try out. Seems like this guy really is pretty good, right? Master Theorem's kicking butt. Why Why do we even bother having lecture 1? We could have skipped right to this. Why do we have lecture part 1, I should say? We could have just skipped straight to part 2. This stuff's working great. Well, apropos of nothing, let's just try out this next example and see how master theorem does for that one. So looking at this guy, we have, again, a equal to 4, a b equal to 2, and f of n equal to n squared over log n. Okay, it's a little weird, but we can do that. Oh, okay, well, we know what this is. N to the log base b of a is just n squared. We figured that out in the previous 2 examples. Done. All right. Now we're comparing these 2 guys. Which of these is faster growing, or are they the same? Well, n squared is definitely faster than n squared over log n, right? Just thinking about it, that log n is going to be a positive number bigger than 1 once, n gets big enough. This is going to be a positive number, so this is going to be shrinking this. So I think non-controversially, as we're thinking about this guy, I can immediately say this is not case 3. This is not case 3. Just because this one is growing, if anything, slower. Then you're like, okay, is it case 2 or is it case 1? Oh. Well, I don't know. Let's just try one. Let's see, case 2. Well, case 2, these 2 would have to grow in asymptotically the same rate. So we say, well, maybe it's case 2. So f of n in this case is n squared log n. And we're trying to see, is that tightly bounded by n squared? Again, you might find yourself kind of stumped as to how to prove this, but we can use good old limit theorem. Remember this guy from a couple lectures back? Yeah, lecture 2. Limit theorem. And limit theorem tells us we can look at whether the limit as n goes to infinity of kind of the ratio of these guys, whether that goes to a constant. If these 2 are asymptotically equivalent, this will go to a constant value greater than 0. So a constant value not equal to 0, right? And so we can, well, let's see, we can reduce this a bit. Let me flip this. So if we think about it, this would go in the denominator, right? If we were to merge these, merge these sort of this guy into the top fraction. Just good old math trick, right? So we would be like multiplying by the reciprocal of this, so it ends up in the denominator. Okay, well, that's good, because that means we can cancel stuff like that. Oh, and then we have a limit. Okay, got to put our calculus hats on. Recalc hats, maybe. And we look at this and we say, okay, well, what's the limit as n goes to infinity of 1 over log n? Well, log n is really slow growing, but it still grows forever. So log n, by itself, its limit is still going to take it to infinity, right? If you do the limit as n goes to infinity, log n still goes to infinity. So this is going to end up being actually 0. Yeah, because the denominator gets bigger and bigger and bigger and cancels out our numerator, and the asymptote, the thing it will approach as n gets bigger and bigger and bigger, is 0. Consequently, we actually just proved n squared over log n is actually in little o of n squared. And it cannot be the case that they're tightly bounded. So, nope, can't be case 2. Well, it seems bad because obviously we did a bunch of work and it didn't give us the solution. But the good news is, hey, we only got one case left, right? It's gotta be case 1, we say to ourselves. Oh, okay, case one, let's try it. Obviously, this, we want to prove that this guy is upper bounded by n squared minus an epsilon. This sounds pretty easy. We just proved that n squared is strictly upper bounding this guy. So we really need epsilon to just be the difference between this and this. Maybe another way to put this that maybe is a little easier to grok, to read, is to think about this as n squared over n to the epsilon, right? This is the same thing, just a different way to write it. And this makes it really apparent that the difference is really this versus this, right? So in a sense, what we want, and sorry, I know I'm below the line here, let me pull it up. We want to find a n to the epsilon that's roughly the same as log. If we can, then we can just cancel out that difference, right? Between the left half and the right half, the left-hand side and the right-hand side. Well, now you ask yourself, is this true? What's log n? Like, we can choose epsilon equal to fractions. So you might ask, is log n around like n to the 1/2? Or maybe we could make it even smaller. We can make, is it log n around n to the 0.0001, right? Well, it turns out n to the 1/2 is much faster growing. So this is not true. Actually, this is much faster growing than log n, right? N to the 1/2 is going to be too much. We're going to be dividing by too big a number. You know, if you haven't seen this before, this is a nice way to write much bigger. A more mathematical way would be to prove log n is in little o of n to the 1/2. But I'm gonna skip that. I'll trust that you believe me, and if you don't, you can graph it yourself and see. The interesting part here is that log n compared to like n to the 0.00001, you would think, well, if I just keep adding zeros, eventually I'll get there. Nah, turns out that doesn't work. It's actually, again, log n will be much smaller than n to the 0.0001 for large values of n. And that's because log n is exponentially slowly growing. Sounds weird to say it that way, but it's like growing exponentially slowly, whereas this guy is only growing polynomially slowly. So inevitably, this guy is going to grow a bit faster than the log, yeah, no matter how many zeros I stick in there. So this doesn't work, this doesn't work, and actually there is no way to make this true. And so case one is also not true. Oh, oops, that sucks. Turns out none of our three cases applies to this example. So this is where it gets into, you need those techniques we learned earlier, and you need a sense of the runtime if you wanted to analyze something like this, right? It's unfortunately not enough to necessarily use master theorem. Now, there's some extended rules to master theorem you can learn that will help you, but there's sort of always going to be these cases on the outliers that don't quite work for master theorem. So we want to be able to understand what master theorem is doing or how to do that same stuff ourselves. Okay. Any doubts about this? Maybe for fun, in one of our lectures, we can sit down and try and actually estimate the runtime of this guy. That sounds like it might be amusing. For now, though, I think I'll leave it here since this is just supposed to be about master theorem itself. And we'll come back next time, and we'll think about some more divide and conquer algorithms. Now that we know how to analyze them, let me show you all kinds of stuff you can do with them, since they're so cool. All right, thank you so much, folks.